Hi, my name is Genki Miyauchi, and I'll be presenting our work, which is titled Multi-Operator Control of Connectivity-Preserving Robot Swarms using Supervisory Control Theory. Human-swarm collaboration is an important topic for deploying a swarm of robots in the real world. Potential scenarios could be the exploration of an underground mine or search and rescue missions, where the robots are working alongside the human operators. We are specifically interested in the case where multiple human operators are sharing the control of a swarm, as it can be beneficial or even necessary to have multiple humans in scenarios that exceed the capability of a single human. Challenges in human swarm collaboration can arise from scenarios that lack global communication or positioning available to both humans and robots. And communication is crucial for multiple people to work together. The problem that we look at consists of a bounded 2D environment. The red regions indicate the tasks that need to be completed. The big number in the tasks represents the amount of work to complete. There are two types of agents in the environment. The lead agent is a representation of the human operator, and there are two lead agents in the environment who can instruct the robots to work on a task. The workers are robots that are capable of performing the tasks. Both the lead agents and workers don't have access to their global positions and can only communicate with their local neighbors. The goal is to minimize the time to complete all tasks while also preserving the connectivity between the two lead agents. We use a leader-follower approach, where each lead agent is followed by a group of workers to form a team. We refer to a worker in a team as a follower. As the lead agents move away from each other, some followers will leave the team to become a connector to maintain connectivity. Similarly, when the lead agents get closer, some connectors will become redundant, so they will rejoin the team that's nearby. To develop the robot's control logic, we use supervisory control theory, a formal approach for controlling discrete event systems. We express each of the robot's capabilities and specifications as a formal language you see on the right. The control logic is then obtained from these languages in an automatic fashion. From previous work, we can also directly produce source code of the control logic, which helps in reducing the amount of ad hoc development and improving portability to other robot platforms. The SCT models designed for this work are described in the paper in detail, so please check it out if you are interested. Here's a simulation running in Argos. The two lead agents and workers are initially clustered near the center. As the simulation starts, the lead agents each head towards the tasks at the bottom. When the distance between the teams gets too far, some followers become connectors to form a chain. Once a lead agent arrives at the task region, it signals the workers in its team to perform the task, which can be seen by the amount of work decreasing. Apart from maintaining communication, the robot chain is also used to rebalance the number of robots in each team. Here, the task in the center requires at least 15 workers to complete. The lead agent sends a message requesting for more workers to the other team. The lead agent in the other team receives this message via the chain and decides to send 5 workers. These workers will travel along the chain to reach the team on the other side, which then satisfies the required number of workers for the task. In summary, I've presented a formal method for two human operators to exert shared control over a swarm of robots. The robots autonomously formed a connectivity-preserving network to allow the operators to share information and robots. We hope to extend this method to more than 2 human operators and perform studies with human participants and real robots. Thank you very much for listening.